basically the only kind of functions we have learned how to differentiate are polynomials and other functions where that consist of sums of something to the power something, right? And this includes the square root, because the square root is the same as x to the power half. And we can also have functions like minus 1. But let's just imagine we have some function. Two functions. F of x equals, say a number.
15.
15. Times power x to the power what?
3.
3. Plus square root 5, no, not 5, x. Minus 10. So this is one function. Let's take another function. What should this be? You say a number?
26.
26 to the power
5.
plus or minus something.
16.
16 times something.
6.
Yes.
X cubed.
X cubed. Yes. So
X cubed.
these are fairly simple functions, right? So we had rules for differentiating functions. F plus g, the sum of these. You said cubed?
Yes.
Sorry? Cubed.
I'm just having trouble reading it.
Ah,
If it says 26x
5
to the power 5.
Oh god, that's to the power 5.
Yeah.
So if you have a sum of two functions, if you take the derivative of that, you should just take the derivative of each function and add them. Right? That was one of the rules. Another rule was f times g, the derivative of this, and this was the somewhat more complicated rule, called the Leibniz rule. And here it's important that these are actually primes and not just some leftovers from a previous lecture. Then we had the fraction of two functions. The derivative of this was f prime of x, g of x minus f of x, g prime of x over g squared of x, where g squared of x is the same as this. That's what we mean by this. And then you had that if you multiply it by a constant, so this is now a constant, this is just c times the derivative of it, like this. Oh, that should be a prime. So how can we apply this to these two functions? First of all of these needs us to be able to find the derivative of the functions themselves. Right? So we should start by finding, if we want to find the derivative of their product or something like that, we should start by finding f prime of x, right? And what is this? Well, wait, you're going too strong, too fast. So the problem here is that this rule tells us what? It tells us that if we have the sum of something, we can take the derivative of each of them. But here we have not just two terms, but three terms. This is in principle also something we have. But it's very easy to see that if we can do this once, we can also do it twice. So we can think of this as... Are you recording this?
Yeah.
Okay. So let me just write it down here. So f plus g plus h. If you take the derivative of this, then it's possible to consider it as the sum of two sums, right? Like this. So it's f plus g prime of x plus h prime of x. And then we can use this, split it up, so it becomes Normally you don't do this, you just say, well, if we have a sum, we can just go from this to this, but now we've actually thought about how it works. And you can see that it's actually just an extension of the rule we have over here. So we should take all of these terms and differentiate them individually. Now this thing here, how can we differentiate that? Well, we can differentiate it because we know that we can differentiate a constant times something we know how to differentiate. And we know how to differentiate x to the power 3. Right? So this is 15 times 3 times x to the power 2, right? Which is, as someone said, 45 to the power times x to the power 2. Then we have a square root 2. No, not x to the power a half. So square root x. We pull down the half, and then we should put x to the power 1 half minus 1, which is the same as something more complicated. We can write that in the next time. And then lastly we get the derivative of minus 10, which is 0, right? So this is 45 x to the power 2 plus, and then this becomes x to the power minus a half, right? But when we have something which is to a negative power, it's the same as saying 1 divided by it. So we get this, and then we should remember the 1 half out here, but we can incorporate that in the fraction, and we get this. So this is the derivative of f. The same rule as we used before applies again here. So g prime of x, that's 26 times 5 times x to the power 5 minus 1, right? This is just a constant. This is something else, blah, blah, blah. Plus 16 times 3 to the power x to the power 2. And what is this? This is something like this. 130?
130 and the
Oh, yeah. Okay. Yes, you're right, of course. I multiplied by 6.
48.
48 x squared. So now we have the derivative of f and we have the derivative of g. Now, if we take the sum of these two functions, I would just have to take the sum of this and that. Right? That's simple enough. But how do we find the derivative of their products? So f times g, the derivative of this. What is this? Well, we should just use this rule, right? We should take the derivative of this, which is this, 45 x squared plus 1 over 2 square root x times g, not differentiated, 26x to the power 5 plus 16x cubed plus, where we leave f as it was, 15x cubed plus square root x minus 10 times the derivative of g, 130 x to the power 4 plus 48 x to the power 2. Now what one could do is to multiply these parentheses with each other and get something long and complicated. I mean, it's not difficult, right? It's just doing it. Something else we could have done was to just multiply these functions first and then finding the derivative. And we would get the same result, of course. That's the point. But now we have illustrated how to use it. The only one we haven't used yet is this one. So let's find the derivative of this. So f over g everything differentiated. What is this? Well, it's the derivative of the first one is 45x squared plus 1 over 2 square root x, parenthesis, then g undifferentiated, 26x to the power 5 plus 16x cubed. Agree? And then minus f, so that's 15x to the power 3 plus square root x minus 10. And this should be multiplied by the derivative of t, which is almost too big to be on the blackboard. I'll just write it slightly smaller. I mean, it's written up here, right? I'm just trying to illustrate that it may look complicated, but it's, I mean, it's just going forward as you're taught to write. There's nothing difficult about it. And then everything divided by g squared, right? So it's 6 to the power 5 plus 16 x to the power 4. And there you have it. So this is the derivative of this horrible function. Do you want me to go through other examples, or do you have any questions that would be relevant for everyone to know? I had quite a few questions from the last exercise session about how to evaluate sine of minus pi third, something like this. Did you all figure out how to do this? Anybody who didn't? Also, there were quite a few questions like, find out what this is. Here the trick was, I mean, always when you have these things, it's good to try to visualize what are we actually dealing with. We're dealing with 5/6 of a pi, so it's slightly less than a full pi. Right? And a full pi, it's a bad name in English, right? It's not a full pi, it's only half a full pi, if you think of it as a pie chart. This is a pi, this kind of pi. And then what is missing? Well, you're missing this, which is pi 6th. So, if you want to find the exact value of that, you should note that, well, it's the same as finding sine of this, right? So, what we have actually just rediscovered was what I said last session, that this, if we rewrite it as pi minus pi 6th, which we can do, right, because this is the same as 6 pi divided by 6 minus pi over 6, and then we get this, right? So it's just a complicated way of writing the same. And then I told you last session that this is the same as just taking sine of this number here that you subtract from your pi. So this is just this. And then you can look this up in your table. It turns out to be 1/2. So try making these diagrams or pie charts. Okay?